the session because it's exactly okay. Okay. So welcome to the day 3, session 7A, non-SQL modeling and applications. And this section consists of one invited lecture followed by the three contributed lectures. And the chairperson for this talk is Professor Mehul Malik, Professor of Physics at Institute of Photonic and Quantum Sciences, Heliot-Watt University, Edinburgh, UK. And his research interests includes quantum entanglement, quantum imaging, quantum information, and high dimension.
You are muted, Justin. You are muted.
So some of the awards are EPSRC Early Career Research Fellow, Marie Curie Postdoctoral Fellow. He got a H index around 31 with the citations around 3,684. And he also won experimental physics working in the field of quantum optics and the quantum information. So with this introduction, I request Professor Mehul Malik to chair this session.
Okay, great. Thank you, Justin, for that nice introduction. I can't say I've ever been introduced with my H index before this conference, so it's okay. So let's begin. Welcome, everyone. I believe this is the last session, one of the last sessions of the conference. So let's get started. So the first speaker today, let me introduce, is Professor Ranjit Thapa from SRM University in Andhra Pradesh. Ranjit works on a variety of different things involving 2D materials, nanoparticles, and today in particular he will be talking about using quantum mechanics and machine learning techniques to study catalytic reactions. So I'm very curious about this because it's somewhat related to my field as well. So with that, Ranjit, why don't you go ahead and start?
Yeah. Thank you, Dr. Malik. So I will share my PPT. Yes. Yeah, I think it's visible.
Yes.
Yeah. So good afternoon. So first of all, thanks to organizer for inviting me and Dr. Malik for introducing me. And it is my pleasure to introduce our current works on this topic to this audience. So particularly here, I will focus on particularly a journey of how we have defined some descriptor and how we can explain or find the new materials using quantum mechanical tools and machine learning approach. So here I will go directly about our group. So we are computational science group, of course, working in energy generation and storage and environmental problems, and particularly catalytic materials and other materials. So these are the three major area where our group is working. And these are, sorry, I think there's something happened.
I think it's okay now.
Yeah. So this is the three area where we are working, and of course I will focus on this one which recently we have published in this article. So let's go ahead about that. So what was the questions? A lot of questions in our mind around 4 or 5 years back, that why doped graphene or carbon act as a catalyst for ORR or OER or anything? And can we define any structural descriptor which can explain the catalytic activity of graphene? Or can we define an electronic descriptor based on the particularly the electronic properties? Can we define it so that it can explain all the properties of graphene as a catalyst? And how really machine learning can help in this prediction? So this is overall the questions we had. I hope we have given in this last two works. So it was the work one which published in almost 2018 January, So where we have given a structure electronic descriptor, I feel it is a discovery because we have defined it as electronic descriptor which can really explain any type of carbon-based material for any type of reaction. Of course, we have considered ORR in this first work. And the second work, which is the focus of current talk, is how we have done like QN and ML approach, which can predict the carbon-based catalyst and what are the energy parameter and electronic descriptor. This particularly the work 2 I am going to explain here. So let's go ahead. So these are the overall carbon-based descriptors defining on different electronic property was starting from February 2014, and researchers wants to understand why really the carbon or doped carbons or any doped carbon-based materials, it could be graphene or CNT, is a catalyst. So particularly for different reactions, different electronic structures or different electronic properties has been proposed. And in December 2017 we also proposed a pi electron based descriptor. Like if you really find out what will be the pi electrons occupancy of that carbon atom, you can easily explain the catalytic property or any other properties of graphene. So this is the work 2. So what was the question? It is important to understand the potential determining step which define the activity. So we have to first do that. Like which intermediate is really governing the properties of any carbon-based catalyst, which leads to a very good catalyst for OER or ORR like that. So we understand that oxygen is very important, playing a role in the intermediate. And to find the identical carbon catalyst in a large material space, like if you do a lot of calculation or experiment, it takes a lot of years to come to define a new catalyst. So how we have reduced is that we will introduce in this work. So this is the overall, you can say this is the structure we have taken. Of course, a zigzag and armchair graphene nano ribbon of different width, and of course different type of dopant like SP, SO2 and PO2 dopants we have taken. So if you do this combination, so how many combination you can really make it like a model structure. If you consider 9 with 7 type of dopant, and if you have to calculate 7 site, that actually you have to you have a model, or you need to have a site of 441 sites. And if you have to do 3 calculations, that means you need 1323 relaxations using quantum mechanical calculations. And for particularly for zigzag one, if you have 18 with 6 dopant and 7 site, altogether it is 2268 relaxation. This is an example. If you increase the number of dopant, or if you increase the width, it will increase more. So this is just 2 type of graphene structure. I can say you that how many calculation we have to do to predict which is the best catalytic center, which is the best catalytic site or structure. But what we have done is we have done only 115 model structure, of course 500 relaxations, and then we predicted using our analytical equations, and also then machine learning predictive model equations. And then we have shown that we don't have to do the DFT calculation to predict that, and the accuracy is really good. If we go another, so this is the problem which I'm going to define. And this is the things where actually the energy parameters, this is the free energy change of O and minus free energy change of OH. This is termed as the energy parameter of OER, whereas for ORR, the delta G OH is the energy parameter for ORR reaction, which is oxygen evaluation reaction, OER and oxygen reduction reaction. These reactions are very important, particularly for the fuel cells, metal air batteries, and a lot of applications are there. But we are going here to focus on the fundamental, that why these 2 reactions, even their reactions is back and forth, why they are really different in the energy parameter. Why one for OER energy parameter is this one, and ORR this is the energy parameter. Then we have find out that particularly this is the reaction step. If you see, then we have find out that there are the 1, 2, 3rd, and particularly you can see that if third reactions cannot be explained, reaction means intermediate state cannot be explained by your particularly this third reaction cannot be explained by the delta GOH if it is your energy parameter. So this is the things which we understand, that means why we need this is an energy parameter, because your third step is the main one. And this volcano plot, particularly this is known in our catalytic, which is the best catalyst, will be in the top. So if you understand, this is the over potential. So this volcano plot can be easily understand only by this type of energy parameter, and we can define this as using another energy parameter. But overall, these two relations are similar. Here we want to emphasize that oxygen is the main intermediate which playing a role in the OER. And we have proved also with respect of electronic structure that how the intermediate from O to OH, when we are going, how the electrons are really given back to the surface, and which leads to the main energy parameters of that reactions. So like that, when we have plotted the relations of different energy parameter, we have find out that they have a very good R-square value goodness of fit. That means whatever we have predicted is a very much correct, and our oxygen playing a very important role to define the OER activity. So this is another one that, of course, binding energies also you can take, and you can easily match that. You can easily find out that which catalyst is the best catalyst using your energy parameter reactions. So now we will go to the next part where we will understand the descriptor. Like what I was telling, now I will reduce the number of calculation using our electronic descriptor using QNML method. So as we define that OH ion, particularly the delta G OH ion is important, and delta G O is important. As we already said, these two are the delta G O minus delta G OH. This is the overall quantifying parameter. As any descriptor which you are defining, it should have a linear relation with your descriptor plus this quantifying parameter. That indicates that your the descriptor should have a linear relation with your quantifying parameter. So what could be the descriptor? As in work 1, we have shown that pi electron at Fermi level and pi electron occupancy, which is like if you plot a density of state, simple density of state of a single atom, then this is your pi electron occupancy area under the curve, and at Fermi level is your pi electron at Fermi level for that carbon atom. So if we take like that, different type of parameters we have chosen, and we have defined two type. One is this D means double carbon, S means single carbon, and there are 1, 2, 3, and 4. These are, you can say, these are the features also I can take in machine learning, and here it is the parameters which we take as an analytical model. And as I have not having that much time, I will not explain everything. So d pi is here, which we are defining, and O pi is the occupancy of the pi electron. Then what we have to calculate for each atoms this occupancy and pi electron at Fermi level. Once we do it, then if I match this one with your delta GOH, you can see that R-square values is matching, and slowly we are going towards the proper our proper predictive model equations. How we have done? We have calculated FP1 by this linear equation. For each linear equation, there will be always y equal to mx plus c. Using these equations, we have analytically solved that how we can easily find out a equations, which is this one, where if I only calculate this, I don't have to do any DFT calculation to find this delta GOH. I will only calculate only a bare surface. I don't have to do for adsorption one, and I can easily predict what will be the free energy change of that OH ion or O ion. So overall, this is the things, and once we have this F1, F2, if I solve you, F1 is equal to this 7.4, this is all mx plus c. These slopes are coming from here. If you plot here, everything you will get from here, this curve, and then F1, F2, and this. So it will lead to this equation. This leads to this equation, and you will get a delta GOH and O. And if now you have to find a quantifying parameter, as I'm telling, this is the energy parameter. Now I have an equation. I have developed an equation. This is just an analytical way, just a simple way we have defined, and we have now what? This is energy equal to some parameters plus suppose, which is known as suppose m into x1, x2, m2 into x2, like that we have defined. We know x1, x2 because if you only calculate a surface, you can easily predict how much will be the pi electron of that surface. That means you don't have to calculate much on that. Like you don't have to absorb oxygen, you don't have to absorb OH, you don't have to do further calculation, just simple a calculation of surface, and you can easily find out what will be the value. You can easily find out what will be your over potential, because this is the line. If your value of, suppose if your value of over potential is this, then where is that? Sorry. Yeah. So if your value of over potential is this, then or delta GH is this, then your over potential is 1.1, like that. So that means here what we have done, we are now defining electronic descriptor by analytical methods, and we have predicted very well. This is the calculated one, which is using this equation and using DFT. And we have find that R square value is 0.77. You can easily see that how much is this analytical equation is matching, and which proof that yes, our descriptor theory is correct, and pi electron is a descriptor like a d band center in metal, like a d band center in metal. Similarly, pi electron is a descriptor for our carbon catalyst. So after this, what we can do? Then we have considered multilinear regression and support vector regressions, of course, machine learning techniques, and where we have considered these 4 features, which is known features. We know that yes, this like we have not taken randomly any features. We have considered this as our known features, and once we predicted and using multilinear regressions, if you do your training and test sets, we are getting better than the analytical which we have fitted by our equations. And for SVR technique, it is much more better. So this is overall, we have shown that if you consider this as a feature and you use now machine learning technique, of course your predictability is increased considering the DFT delta GOH O minus delta G. This is of course over potential means activity. This whole application will be on this. So overall the SVR how much is calculating, and DFT how much calculating, the training and test sets are really matching very well. So if I go to next, like how much is the R square value for different technique of MLR and SVR and random forest and kernel ridge regression relations. So you can see that our MAC and MAE values are really low, particularly for the support vector regressions. It is very well accepted that it could be a very good algorithm to define the catalytic activity of our carbon catalyst. So after this, we have proved that yes, our descriptor, and it is also versatile, because you choose any of this technique, it is matching very well and you can predict it. So overall, these are the overall conclusion that yes, third step is the supposed to define as the catalytic activity of carbon. Role of oxygen intermediate is identified, and simple and general electronic descriptor is identified to define the catalytic, and predictive model are developed using machine learning algorithm to find site-specific OER activity. So after that, we have did little bit more. I will tell you what we have done. So what we have, in a very short, we actually, if you want to find out the activity of each site, you have to do 55 calculation in DFT. It may require 1 month of time to do that, but in one day I can do only 2 calculation and I can find which is the best catalyst using my predictive model equation. I don't have to do much. So this is like I have reduces from 55 calculations to 2 calculation, and prediction is very high. I will show you how much is that matching is with the experimental results and everything it's matching. I will show you. So this is the very things that you have to do 55 calculation, but with our theory, you have to do only 2 calculation and you have to put in that predictive model, and it is matching very well. And now what you have, suppose is your predictive model is only for that 5,000 sites or 5,000 or 4,000. No, you take a random one, like we have taken SO2PO2. We have never taken during the testing or training data like that. So we have taken a random one which is not in the training or testing sets. We have taken, and we can see that how much is the R square value, and even SBR is a very good prediction capability using this only this 6. If you increase, of course, it will be much more better. So it is like we are not considering any surface or sites which is on that 111 site we have considered for training and testing. It is something different, but the equation is matching, the predicting is very well. Second is, so you can see R square value. So what I'm telling, so you have taken DFT equation. This is our own equation which we have defined using our analytical model. So so how much is the DFT value and how much is the other value, you can see, and mostly the SVR is matching very well. So overall, I can say that for our case, SVR algorithm is really working very well, and the predicting capability of over potential, which need a lot of years, maybe 4 years to 5 years to find out, we can do it in a 2 months, 3 months, that which could be the best catalyst out of 5,000 catalysts. So this is the power which we have shown. And why this is important? Because we have defined the fundamental descriptors, not random descriptors or features, I can say. Then with the experimentalist like that, we have defined, we have compared which are the best catalyst as per today's, which is the potential determining steps. You can see that really this is the we find out that this is the structure which experimentalist can try to make it so that it could be a new generation, a new catalyst for OER. So, and then one question, of course, this was not there in our work. Then reviewer says that this is just a S and SO2, PO2. If you take a random any other type of dopant, your predictive model will work or not. Then we have shown that if you take a nitrogen dope random, we have not considered in that work any nitrogen dope. Then we have find out, you can see that R square value of DFT calculated for these sites and SVR methods, if we calculated using the SVR, if we calculate, then it is matching very well. So that means it is not only for any specific dopant. You choose any random dopant, you can choose any type of weed and edit anything, it will work. So this is the overall things which we have shown that how our predictive models are working in this particularly. Even this is a random dopant. We have never considered before during making that model. So this is the overall, of course, the first part which I want to say. And of course, whatever we are doing slowly, we are trying to put in one of our package which we are building in our own lab through ACRB project and BRNS project. So this is the project which we are trying to do. Of course, a very big versions are already available over the globe, but we are only focusing on this type of catalyst and some specific applications. That's why this package will be important for industrial applications. So these are the guideline how you can. So this is the IP address. You put this IP address, you can sign up in this. Once you sign up, then you can go to the login page. You have to put the email ID and password. And if you forget the email ID, you can get back again. And then you will get a window like this where you will have a solar material, C oxidation, OER, HER module. So if you can periodic tables and other things. So if you can click in any of this C oxidation on OER. So we are trying to add one by one materials here. We are very low in numbers, 100 maybe around. So if you click to get a specific module, you have to click here, then you will get which are the catalysts, which follow which type of reaction, which type of it is either Sabatier activities, it is LH mechanism or ER mechanism. Lot of things, information you will get in our this database. So this database is slowly growing. Specifically, why I'm telling this is very important, because we focus on mainly till now in C oxidation, OER, ORR, and HER, and of course NRR will also come up in future. So these are the particularly now we are making this where the experimentalists can get the information for these materials. So this is the almost the last slide, and after that, so here actually it is very interesting because we have currently have understand that like this NRR is a big problem. So HB process was there which is used to break the nitrogen bond and reaction with hydrogen to make ammonia. So, but scientists wants to, and they are reporting in the last 5-7 years or 10 years that electrocatalytic NRR could be a very good materials. But the fundamentally everyone is doing randomly. So what we want to define a equation and condition which will predict out of a lot of space and everything. You can predict easily that in which area you will. This is the area where you need your catalyst should be, where HER reaction will be probability will be 0 and NRR probability will be high. So there is some conditions equation I'm not showing here. So we are working on that. So that NRR work is the upcoming work from our group, which we are defining equations which can explain that which catalyst will be the best NRR catalyst for the single atom catalyst we are initially trying. So it may solve the long problem, 100 years long problems through this equation and condition what we are thinking. At last, I want to acknowledge our collaborator, Professor Wagmare, Professor Purujana, Nozungpa, Professor GP Das, and Professor Kawazavi, who is also in the audience, and experimentalists, Professor Guntur, Uday, Balchandra, Devolbrato, and some of the from Jain University, and HPCC facility for giving us a very good facility by SRM IST to run all the calculations, and of course the funding agency. Few of the projects is going on like BRNS and ACRB, and of course my own university for providing a lot of opportunities like GRF and other things in my group. With this, I want to thank. Hello.
Yes.
Yeah. So I completed.
Okay.
Yeah.
Thank you, Ranjit, for a very interesting talk. Are there any questions? Please feel free to unmute and ask a question or post your question in the chat. So maybe I'll ask a question, Ranjit, while people are possibly, thinking. I mean, as you know, machine learning is quite useful for many fields. It's used a lot in condensed matter physics as well as photonics, and also for in computer games. So trying to get computers to beat humans, the best human players in games, right? Go and things like that. So I'm just wondering, like, how much can you push this further? So, for example, in the field of machine learning, there are companies that use more recently they're using techniques such as prior information. So you can kind of add to your code some prior information that allows your algorithm to perform better. So is there prior information that you can use that will allow you to sort of expand this search or these algorithms to more complex problems?
Yeah, actually, what we have used is a very simple technique, and it's a regression technique. It's a very basic one. But what we feel that actually, if you have a better algorithm, then your predictions capability will increase. And in here, we are, of course, it is a supervised learning technique. That means we are giving the prior training and then testing. That means that is the define. Only thing is that if in future what will happen that if we have really a very good and a lot of amount of data of materials, and also if your model is good, then there are a lot of chance that we can predict the materials very fast, which could be the correct one, because a lot of things like quantum mechanical calculation we cannot handle in our computers. Even one calculation take a lot of time. Then if it is a 5,000 calculation, how much time we will take? So in that way, the predictions capability for any materials, it could be catalyst, or it could be a solar applications, or it could be a like a hydrophobic capacity, hydrophobicity of your any surface. So everything is possible. I think it is possible that if you give more correct training, or training model should be correct, then your, of course, your testing capability will increase.
Yeah, the other thing that I wanted to just point out, just a comment, is that the field of quantum simulation, right, is trying to do what you are essentially trying to achieve on a classical computer, but they are trying to do it, they can only do it with very small scale systems. So hopefully one day this, you're hitting a computational barrier could be overcome by the field of quantum simulation on quantum computers. And that's the kind of thing that I work on.
Yes, I know. Actually, I taught this time quantum computation little bit, so I know up to DAS algorithm, and yes, that SOAR algorithm. So
Right.
yeah, so I think if that algorithms till now have to be proved in reality.
Yeah, actually, before you get to quantum computing, quantum simulation is much simpler. But anyway, somebody's trying to turn on their video.
Yeah, Professor Kawasabi, I think.
Let me see if I can.
Yeah. No, it's not possible.
Maybe if you click your video.
Okay, thank you. No, okay, thank you.
You have a question, Professor Kawazoe.
Yeah, it's good to in the future, as you said, quantum computing, everything. Yeah, we should work for that. But the present situation, it's not easy for such kind of new technologies. It is based on the assumption that the problem is fixed. We want to see some better situation for general computing. The big change for the quantum computing is necessary.
Yeah, I agree.
Yeah. Thank you.
Okay, thank
Yeah.
you, Ranjit.
Yeah.
Let's move on to the next to the contributed talks. So the next speaker is, let's see, right, H. Seshagiri Rao. And are you here?
Mr. Rao, Shashwagiri Rao, are you here? Okay, Professor, we can move on to the next candidate, Mr. Navami Sunil. I think he is present.
Navami Sunil?
Hello, sir.
Okay, so why don't you share your screen, and in the meantime, I can just introduce your talk.
Navami Sunil, please switch on your camera also.
Right, so Navami is going to talk about bimetallic silver nitrobium anchored graphitic carbon nitride nanosheets-based electrochemical sensor for uric acid detection. It's a long title, but I think this seems to be quite normal in this field. Right, so Navami is from the Nanosensor Lab at the PSG Institute of Advanced Studies in Coimbatore. So please go ahead, Navami.
On bimetallic AGND anchored graphitic carbon nitride nanosheet.
Could you, we cannot hear you. Can you speak a little bit closer to the mic, maybe?
Yeah, okay. For uric acid detection under the guidance of Dr. PBG, PSG Institute of Advanced Studies. So in this slide, I'll be explaining the relevance of my work, that is the need for uric acid detection. And uric acid is 268 trihydroxypurine, and the normal uric acid level range from 2.4 to 6 mg per dl in female, and 3.4 to 7 mg per dl in male in blood. Then the excessive concentration of blood, excessive concentration of uric acid in the body can lead to a condition, and it is called hyperuricemia. And the reports have shown that this can cause a large number of health issues, and one among them is the renal calculus, which is commonly called the kidney stone, in which small stones accumulate in the pelvis region, and due to the excessive or high level of uric acid present in the body, and the size of this can be varied. That is called renal calculus. And the next one is the Lesch-Nyhan syndrome, which is a condition which is characterized by neurological as well as behavioral abnormalities due to the overproduction of uric acid in the body. Then next one is the preeclampsia, which is a pregnancy disorder that is characterized by high uric acid concentration and high blood pressure also. Then the high level of uric acid in the body can lead to the deposition of this uric acid, deposition of this needle-like crystals of uric acid, especially in the joints and all, which causes redness, then paining and tenderness in these joints, and this condition is called gout. Then polycystic kidney disease, heart disease, then type 2 diabetes are some of the other common diseases which are caused due to the high concentration of uric acid in the body. So that is the need for uric acid detection. Then coming to the objective of the work, the major objective is to develop this bimetallic AGND anchored graphitic carbon nitride nanosheets for the electrochemical detection of uric acid. And the specific objectives include the selection and preparation of the material, then the structural, compositional and morphological characterization of the material, followed by the electrochemical analysis, and then finally the detection of uric acid using this electrochemical sensing. And this is the methodology and the precursors are mixed with polyvinyl pyrrolone, and it is used, PVP is actually used as a surfactant that is used to increase the uniformity of Ag as well as Nd nanoparticles. Then ethylene glycol, we have used ethylene glycol as the solvent, and the whole solution, the mixture is stirred or sonicated till a homogeneous mixture is formed. Then we have added the GC3N4 prepared, and it is prepared by the simple pyrolysis of uric acid at 570 degrees Celsius for 3 hours. And then the solution is sonicated, and we have done the solvothermal at 180 degrees Celsius for 12 hours. And then followed by washing and drying leads the formation of the AGND decorated GC3N4 nanosheets, and as shown here. Then this is the overall schematic representation, and this is the material which we have prepared. Here, this one is the graphitic carbon nitride sheet, and we can see these are the bimetallic nanoparticle, that is Ag and Nd, that got anchored on the surface of this GC3N4 nanosheets. And after the preparation of the material, we have characterized structurally and compositionally of this AGND anchored GC3N4 nanosheets. And this is the XRD analysis of the material. And here we can see the strong peak at 27.62. This strong peak corresponds to the conjugated aromatic ring of GC3N4, and this one is the XRD pattern of NDAG GC3N4, and we can see the strong peaks of AG, both AG and ND, and this shows a good correlation with the existing reports of bimetallic GC3N4. Then we have also done the FTIR analysis, and this one is the FTIR analysis for graphitic carbon nitride, and the peak at 3292, it corresponds to the stretching vibration mode of NH2 groups, that is NH bond. And then the peak from 1242 to 1642, it corresponds to the C double bond and then CN heterocycles, and this corresponds to the GC3N4. Then this is the FTR analysis of NDAG GC3N4, in which we can see the major peaks of C3N4 are suppressed due to the formation of this bimetallic ND and AG. So this from this we can confirm the formation of ND and AG. Then after the characterization of the material, we have done the morphological analysis of the developed material, that is AG&D, decorated with G3N4 nanosheets. And this is the SEM image of graphite carbon nitride, and we can see a layered structure of the G3N4. And after decorating it with silver and neodymium, we can see the agglomerated nanoparticles, and that is the AG and ND got anchored on the surface of the layered structure of GC3N4. We have also done the EDS imaging of GC3N4 and AG, ND, GC3N4, and here are the element with a weight percentage and the strong intense bands of carbon, nitrogen, AG and ND confirms the presence of these elements, the confirms of formation of the material. Then we have done the elemental mapping of ADNG, and as shown in this figure, and the TEM image suggests that the GC3N4 layer, this is the GC3N4 layer, and in that the small nanoparticles of AG and ND got anchored on the surface of GC3N4, and this one shows the diffraction pattern of 002 plane of GC3N4, and this shows the crystalline nature of GC3N4. Then after the confirmation, morphological and structural characterization of the material, we have done the electrochemical analysis, and in electrochemical analysis we have used 0.1 molar PBS buffer as the electrolyte, and we used glassy carbon electrode as the working electrode, and this is the CV of bare GCE. This black one is the CV of bare GCE. Then this is the CV of graphite carbon nitride, and AG blue one represents the CV of AG&D GC3N4, and from this it is clear that a strong oxidation peak is observed at 0.39 volt. And then we have used, we have prepared non-concentration of uric acid ranging from 100 micromolar to 400 micromolar, and we have spiked the sample not for analysis. And from this graph, this is the graph representing the spike samples, and from this graph it is clear that with each spiking the current response has showed a significant increase in current response. So from this it is clear that we can use this this as a sensor for the detection of uric acid. And then this is the calibration curve of uric acid. Then my summary of the work is I have prepared the GC3N4 using simple pyrolysis of urea at 570 degrees Celsius for 3 hours. Then I have decorated the GC3N4 with bimetallic AgND on the surface of GC3N4 using a solvothermal process. Then the developed material has been taken for characterization structurally and morphology using XRD, FTIR, SEM and TEM analysis. After that, the electrochemical studies of the AG, ND, GC3N4 has been carried out. And finally, the electrochemical detection of uric acid at different concentrations was also done. And different concentrations include 100 micromolar, 200 micromolar, 300 and 400 micromolar respectively. And that shows significant increase in current response. And I would like to thank ICONN-2021 for this conference. And I would like to acknowledge my research supervisor, Dr. P. Biji, and my director, Professor P. Radhakrishnan, for helping and supporting. And I would like to thank PST managing trustees and officials for providing me the opportunity and facility for carrying out this research work. Thank you.
Great. Thank you very much, Naomi. Are there any questions?
Okay, Professor, I have a question.
Yes.
Why did you use graphite carbon nitride? What's the purpose here? And please stop sharing your screen and then you can answer. Ms. Sunil. So what's the purpose of using graphite carbon nitride here? And is this the same? Because graphene oxide also can forming the sheets, right? So what's the difference between using graphene oxide instead of graphite nitride, and what's the main role here?
Yes, sir. Actually, there are so many reports of using 2D materials like graphene, multi-volt carbon nanotube, etc. For this purpose, but they have some limitations, means the durability wise, they have some limitations of low durability, then low surface area, then difficulty in integration and all. But so that is why I choose GC3 and 4, and especially because of the 2D structure and means comprising of covalently bonded to carbon and nitrogen. Then it is semiconducting, then non-toxic, biocompatible. Main reason is easily synthesizable also, because with a simple pyrolysis method we can synthesize this GC3 and 4 from urea.
Great. Thank you. Okay, so let's move on to the next talk. The next speaker is M. Umadevi. Are you here?
Professor Uma Devi is still not present, but the earlier speaker, Mr. Seshagiri Rao, is present here, Professor.
Okay, great. Okay, so we'll go back to the first talk then. Yes. Do you mind sharing your screen, Mr. Rao? Great. Okay.
Yes, sir.
So Seshagiri Rao will be speaking about exploring the effect of Jahn-Teller distortion on electrocatalytic activity of MoO3. I think that's molybdenum. You're testing my knowledge of chemicals today. And so Mr. Rao is from the Department of Chemistry in IIT Madras. So please go ahead, Mr. Rao. Thank you.
And Mr. Rao, can you switch on your camera also?
Yes, sir. I'm sharing my screen. Is it visible? Yeah. Sir, I'm sharing my screen.
Okay.
Is it visible, sir?
Yes.
It's visible.
Hello. Yes, sir. Good evening to one and all. Then today I wanted to speak about this, exploring the effect of Jahn-Teller on the electrocatalytic activity of MoO3. Then here the structural diversity of MoO3, that is MoOX, why I refer to X means it may range from 2 to 3. So it opens a very wide range of opportunities for various catalytic applications. Here we can see about this 1D, 2D, 3D materials which have been used in various applications. The main application part is being developed because of the flexibility of this optical and the electrical property. That is, it's a N-type semiconductor with a band gap ranging from 2.8 to 3.6 electron volts, and the oxidation vacancies result in the variation of these electrical conductivities. Because of these composition, morphology, crystal plane, and size, we can see about the various applications of this MoO3 in various diverse applications. And some of the noteworthy applications are being listed here. That is, in batteries, we can see about the application of this MoO3 on the reduced graphene oxide, as well as in energy storage devices as batteries and supercapacitors also. Then in fuel cells, as well as in water splitting experiment. And in the recent times, even it was been applied for the self-charging photoelectrochemical properties, as well as the giant thermal Hall effect in multiferroic applications. Like this, we can see about the most of the applications of this MoO3 are there in the even the recent articles also. The crystal planes of this MoO3, it shows here it is having the 3 phases, that is MoO3, 2H2O, beta MoO3, and then alpha MoO3. Then in beta MoO3 and that hexagonal MoO3 2H2O. Here, in both the cases, we can see that the 2-dimensional layers are being distorted with MoO3 octahedral joined with the vertices. And in alpha MoO3, there is no water molecule. The common thing in all these things is that if water molecule is there, it is just between the layers of MoO3. Whereas if water molecule is not there, then the edge is being shared by the oxygen is being shared between the 2 MoO3 molecules. Then the Jahn-Teller distortion of this MoO3 has been explained in the recent publications that's in nano energy here. That's the thing that I'm just representing here, where it is showing about the distortion angle. It is ranging from 82 degrees, where it should be actually 90 degrees in a normal tetrahedron, but it is going to 82 degrees 88 minutes and 89 degrees 59 minutes in the case of MoO3 and MoO2 respectively. So because of this John Taylor distortion in the molybdates and vanadates. Here, these transition metals are able to grow in a particular plane, and then the planar influence on the catalytic activity is also been studied in the recent times. And some of the noteworthy publications of these plane, how the plane is influencing about this catalytic activity is been listed here, wherein some research groups all over the world, they are being focusing, and the different outcomes have come from each and every group. Some of them, they claim that 100 plane is only catalytically active, and some others say that 010 plane is catalytically active, and in some other papers it's been published as the 110 plane is catalytically active. So here, this is the overall summary of some of the noteworthy publications. And so we started to synthesize this MOO3 in a controlled plane manner using the microwave hydrothermal method, where we have used ammonium morphdate as a precursor salt. We dissolved it in the water and then acidified with HCl. Then we subjected it for microwave irradiation in autoclaves, and the sample were collected, the centrifuged, dried, and then calcinated at 40 degrees centigrade. Here, the sample codes that we have mentioned, it is as ABC, that refers to the 10 millimolar solution, 50 and 100 millimolar solutions that we have taken in the initial mixture. The sample characterization and the catalytic part. Here, going to the thermogrammetric analysis, here on the thermogrammetric analysis, we can see that there is a phase change at 404 degrees centigrade. This drastic weight loss is because of the loss of water molecules, whereas the drastic weight loss here observed at 699 degrees centigrade, it is because of the sublimation of alpha MOO3 over the yeah. So here we can see that there is a drastic weight loss in the case of this MOO3 at 699 degrees centigrade. And so this clearly indicates that alpha MOO3 is existing between 404 and 699 degrees centigrade as stable phase. So this molecular spectroscopic studies we have conducted here using the useful DRS, wherein we were able to extrapolate that the band gap was ranging from 2.66 to 2.69 in our samples. But in the earlier literature, it was been reported as up to 2.8. It was been reported, but here we achieved up to 2.66. And in FTR analysis, we were able to conclude that some oxygen molecules were being shared by the 3 molybdenum centers, and some oxygen molecules were shared by the 2 oxygen atoms, 2 molybdenum atoms in the vicinity. So the same thing is been reflected here in the inside. And then here in the powder XRD pattern, we are clearly able to see that there is a change in the intensity of the X-ray peaks. That is here 40 plane, which is being indexed there. Here we can see that there is a change in the intensity when we compare with the other planes which are being indexed here. And then we are able to show that this particular plane is more in that particular compound, means the growth in that particular direction has occurred in that particular compound when we compare with the other planes. This we claim here with the in the coming catalytic activity. Then the crystallite size has been determined by using the Debasher formula, and the Debasher formula on application on finding here, it was being found that 53 nanometers to 58 nanometers and 65 nanometers were been achieved here. Then on rate field refinement of all the 3 composites here, we were able to see that clearly the rate field, the pattern whatever that were appeared, they were matching with the orthorhombic phase of this MOO3, whereas the line intensities are being checked, and then the chi-square value, it is ranging from 5.66 here, that is indicating about the good coherence between the theoretical and the experimental approach, and hence the crystal morphology that we obtained for these MOO molecules is being listed here with the crystal geometries that has the bond lengths and bond angles are been enumerated here. Here we were able to achieve up to 77.35 degrees, wherein the earlier reports it was been reported as 82 degrees was the distortion angle, and here we got up to 77 degrees. Then the catalytic activity is also being influenced over it. Then the semi-mass and the EDAX spectra here, it is showing that there is a clear we got the pure phase of MOO3 itself, and the carbon whatever that's appearing in EDAX is because of the carbon tape that has been used as the stacking material in the SEM. The electrode preparation for the electrochemical activity was been done like this. The 4 milligrams of MOO3 was been taken and mixed with 40 milligram of Volcan carbon, and it was subjected to intermediate microwave heating for 5 cycles. Later, the platinum in ethylene glycol was added with a loading ratio of 0.1 milligram per ml. And again, on the microwave irradiation for intermediate heating, the samples were collected, they were centrifuged and dried at 80 degrees centigrade. The 4 milligram of the prepared catalyst, that's the platinum loaded catalyst, was mixed with the 0.2 ml of naphthalene, then 0.15 ml of ethylene glycol and 0.2 ml of water. the mixed well and made a slurry, and 20 microliters of the slurry was just loaded on the glassy carbon electrode with 0.6 centimeter diameter, and it was being called as the working electrode. The electrochemical things were being carried out in the aqueous solution of H2SO4, that's 1 molar, in a potential window of minus 0.2 volts to 1.2 volts with reference as silver chloride electrode. Then the CV studies, it's clearly reflecting in the first graph. It is very clearly showing that the different catalytic activity means the CV spectra of the different catalysts that were being prepared with reference to the Vulcan carbon, because we have taken the Vulcan carbon in addition to our material and we have loaded the platinum. So we have even considered the Vulcan carbon as a reference material. Then here we have, it is very clear that the compound that was prepared using 100 millimolar solution had shown a good catalytic activity. And then at the varying speeds of the cyclic voltammetry, we have run the activity test, and then it was very clearly understood that the catalyst was very stable by the cycling. By cycling for up to 50 cycles, we have performed the experiment, and then all the experimental results were almost repeated. This indicating that the catalyst was very stable over the glassy carbon electrode and the coating was good. Then further, for the oxidation studies, it was been observed that the C sample was showing the highest activity. Here, the star mark is indicating about the 20 millivolt per second as the scan rate, and without star mark, it is indicating about the 10 millivolt per second as the scan rate. Then here, it's very clear that the sample prepared using 100 millimolar sample was showing a good catalytic activity. This is because of the in situ mixing and formation of the platinum bronze or the
Mr.
surface,
sorry to
the
interrupt.
charge transfer between the
You have only, Mr. Rao, sorry to interrupt. You have only 2 more minutes, please.
Yes, sir. I'm about to complete, sir. Yeah. Hence, it is observed that the sample C is acting as a good catalyst due to the presence of the high intense planes, that is the 100, as when it is compared to the other planes. This is the conclusion, and this is our research group. And I'm very thankful to the organizers as well as our research group for supporting me for this seminar. Yes, sir.
Great. Thank you, Mr. Rao. Are there any questions?
Thank you, sir.
So that was a very fast information transfer on your part. I think one of the fastest talks I've seen. Yeah, I cannot say that I have a question personally, to be honest. If there are no questions, then maybe we can conclude, and a bit early.
Yes, Professor. I can actually our third talk, the contributed lecture, she didn't join. So I think if in the case she didn't join, we can complete the session.
Has she joined?
Not yet, Professor.
Okay.
Didn't join
Yeah, because I
now.
guess even if we were to start now, we would run into the next session.
Yeah, yes, Professor. We can wind up.
I think we should conclude, and then let's thank all the speakers. Thank you very much. I will clap for everyone. Yes, see you in the next session.
And thank you, Professor Malik, for chairing this session. And with this talk, the session ends now, and the participants please tuned in for the next keynote lecture and followed by the validatory function. Thank you.
Thanks, Justin.
Thank you, Professor.
Okay. Thank you.
Thank you.